In this video, we're going to talk about basic differentiation rules. Our first rule is the constant rule, which says that if you take the derivative of a constant, any number, you're going to get 0 as the derivative because the slope of a horizontal line, so if this is our line here, y equals some constant, the slope of that is 0. So here are some examples. So all of these are constant functions written in different ways, and k is a constant, pi squared is a constant, we all know that. And the derivative of all of these expressed in different ways all equals 0. Our next rule is the power rule. So a power is some function like f of x equals x to some power. Don't confuse that with an exponential function. Those two are different. So essentially what you do is you bring down that n power, or your exponent, down to the front, and you subtract 1 from the n, and that's your derivative. So let's work out 3 examples so you can see what I mean. Let's start with this function. F of x is equal to x cubed. So in order to represent the derivative, I say f prime of x. I bring down the 3 here to the front, and I have x to the 3 minus 1. So that gives me the derivative as 3x squared. My second example is g of x equals the cube root of x. So I'm going to rewrite that, which is a really helpful thing to do when you're writing a lot of derivatives, is x to the 1/3 power. That's a cube root. So g prime of x is I bring that 1/3 down to the front, I do x to the 1/3 minus 1, which is 1/3 of x to the negative 2/3 power, which is the same as saying 1 over 3 to the x to the 2/3 power. And then my last example here is y equals 1 over x squared, which I rewrite to be x to the negative 2 power. So the derivative here is y prime. I could have also written dy over dx. I bring that negative 2 down to the front right here, and I have x to the negative 2 minus 1, which becomes negative 2x to the negative 3rd power, which is the same as saying negative 2 over x to the 3rd power. One application of the derivative is in order to help us find the slope of a graph at a certain point. So let's say I have this function f of x equals x to the 4th power, and let's find the slope of the graph of f of x at each of these points, so at -1, 0, and 1. First thing I have to do is find the derivative of f of x, so that's f prime of x is equal to 4x cubed using the power rule. And so I'm just going to plug in -1, 0, and 1 in for x and figure out what the slopes are going to be. So at x equals -1, this slope is going to actually be -4. At x equals 0, the slope is 0. And then the slope at x equals 1 is positive 4. So you can have different slopes of tangent lines at different points. So that's what the power rule, especially in this derivative, is going to help us do. Another thing that derivatives help us find are equations of tangent lines at certain points. So let's say that I have this classic power function here, x squared, and let's find the equation of the tangent line at x equals -2. First thing that I'm going to do is find the derivative of x squared, which is going to be 2x according to the power rule. And I'm going to plug in x equals -2 in for that to find the slope of the tangent line, which gives me -4. So I know that I can use this equation to find the equation of the tangent line, but I need a y1 and an x1. I already have an x1 here, so I need to plug in the -2 into the original to find the point at which our tangent line is going to cross through on that original curve. So that's the point -2 comma 4. I plug that in here, and y equals -4x minus 4 is the equation of our tangent line of x squared when x equals -2. Here's another rule that comes in handy, and that's the constant multiple rule. So your constant is some c, which is a real number, multiplied by some function, f of x. So all I really have to do is find the derivative of that function and multiply it by the constant. So let's work out these 3 examples to see what that really looks like. For my first function here, I've got y equals 5 times x cubed. 5 is my constant, so my dy over dx is 5, because that's a constant that's going to sit on the outside. Take the derivative of x cubed, and that's going to equal 15x squared when I multiply those 2 constants together. My second function is y equals 2 over x, and I'm going to rewrite that first as 2 times x to the negative 1 power. 2 is our constant, so my y prime, I'm going to leave the 2 on the outside, take the derivative of x to the negative 1, and I'm going to end up with negative 2 x to the negative 2, or negative 2 all over x squared. My third function here, I have f of t is equal to 4/5 t squared, so that 4/5 is going to be my constant. I'm going to take the derivative of my t squared, I get 2t, so 8t over 5 is going to be the derivative of f of t. Let's do 3 more examples, but make them a little bit more complicated. Next function up is going to be y equals 2 times the square root of x, which I'm actually going to rewrite so I can take the derivative as 2 times x to the 1/2. So when I take my y prime, I leave the 2 on the outside, take the derivative of the square root of x, and all I'm left with is x to the negative 1/2 power, which is the same as saying 1 over the square root of x. And next we have y is equal to 1 over the cube root of x squared, which of course I'm going to rewrite as 1/2, so that 1 over 2, times x to the negative 2/3 power. So I'm going to take my dy over dx, leave the 1/2 on the outside, take the derivative of the x to the negative 2/3, and I'm left with this expression here, or negative 1 over 3 times the cube root of x to the 5th. And our last example here is just y equals negative 3/2 x, which is just a line. So I'm really just taking the derivative or the slope of the tangent line that's created there. So really it's just the slope of the original line. So that's how I end up with negative 3/2. Let's pause from the rules for a second to talk about using parentheses when finding derivatives. So if I have two functions here, they look almost identical except I've inserted parentheses around the 2x in the denominator. Let's see if that affects our resulting derivative. So when I look at my final answers here, they look almost identical except for the coefficient in front of our x to the 4th in the denominator. So that's caused by, in this second problem here with the parentheses, I have to distribute that 3, that exponent, to the 2 and to the x. So I'm really left with 5/8 out here instead of just 5/2. So be very careful with parentheses. Next I want to talk about the sum and difference rules as it pertains to derivatives. So what that really means is that if I've got an expression like this first example that we're going to work out in a moment here, is this x cubed, this negative 4x, and this positive 5 are each different functions. So really what I do is I take the derivative of each of these pieces and then I just add or subtract them together based on what signs are in between each function. So now let's work out these 3 examples and see how these rules play out. So for our first example, I'm just going to take the derivative of x cubed, which is 3x squared, subtract the derivative of 4x, which is just 4, and the derivative of a constant, remember, is just 0. So my f prime of x is 3x squared minus 4. Our second example here is g of x. I have this expression, so I'm going to take the derivative of each of the pieces separately, and I end up with g prime of x is equal to negative 2x cubed plus 9x squared minus 2. And then I have this last function here, y is equal to this function, which I'm actually going to simplify first. So I'm going to divide everything by x, and I have 3x minus 1 plus 1 over x, which is the same as x to the negative 1. And so now I have y prime is equal to the derivative of 3x, which is just 3. The derivative of negative 1 is 0, so it's minus 0. And then the derivative of 1 over x, or x to the negative 1, is going to be negative x to the negative 2 power, which, if I simplify it down, is 3 minus 1 over x squared. And here we have the last set of rules for this video. And that has to do with the derivatives of the sine x and the cosine x functions. So as a general rule, if I take the derivative of sine of x, that gives me the cosine of x function. And if I take the derivative of the cosine of x function, I get the negative sine of x function. So a quick little proof on that, if I have this black curve here, which is the sine function, and I were to draw an infinite amount of tangent lines, these blue lines here, they actually map out to be the cosine function. Much like if I took the cosine curve and I mapped out its tangent lines infinitely, it would create the sine function, but because it's a negative here, we know that that's going to be flipped over the x-axis. And finally, let's work out some examples with sine and cosine. First up, I've got y equals 2 sine of x. I leave the 2 on the outside because of the constant multiple rule. Take the derivative of sine of x, which is just cosine of x, so y prime is 2 times cosine of x. Second example here, I've got y equals sine x over 2. I'm going to rewrite that as 1/2 of sine x, so that's my constant on the outside here. Take the derivative of sine, and we know that that is cosine of x, so dy over dx is equal to 1/2 times cosine of x. Our next example is y equals x plus cosine of x. I'm going to take the derivatives of the x and the cosine of x separately, so that's going to leave me with 1 and a minus sine of x. And so this last example here, they forgot the y equals in the book, so I added it in. Y prime, I'm going to take the derivative of cosine of x, which is negative sine of x, and I'm going to subtract pi over 3, because remember pi over 3 is just a constant. I'm going to leave that on the outside as per the constant multiple rule. I'm going to plug in my derivative of sine of x, which is cosine of x, and I'm left with negative sine of x minus pi over 3 times cosine of x. And that's going to do it for this video. Thanks for watching.